ask an AI to, generate a complex financial model or parse through massive data sets, you probably picture all that code executing somewhere up in the cloud.
Right, the magical cloud.
Yeah, exactly.
Yeah.
But what you should really be picturing is a tightly packed row of industrial space heaters just running at absolute maximum capacity.
Oh, absolutely.
Because the cloud is running dangerously hot right now, and the people in charge of the physical buildings housing these systems are, well, they're quietly hitting the panic button.
I mean, the abstraction of the cloud has been this phenomenal marketing success, right? But it completely masks the brutal physical reality of computing. We're basically reaching a hard thermodynamic wall here.
Yeah. So, welcome to the deep dive. Today we are stripping away the software layer to look at the massive, hidden, and honestly physically extreme infrastructure of artificial intelligence.
It's fascinating stuff.
It really is. And to do that, we are analyzing a really comprehensive piece by Courtney Thompson, and he's a sitting chief information officer himself.
Right, which is a crucial detail.
Right. His article is called AI-Ready Data Centers: What CIOs Should Know About the Hardware Behind the New AI Frontier. And it forces us to look at this transition entirely through the lens of an IT leader.
Yeah, the people who actually have to keep things running.
Exactly. The mission of this deep dive is to unpack how the folks responsible for keeping the digital economy online are navigating these, frankly, unprecedented physical and financial risks.
If we connect this to the bigger picture, the entire risk profile for enterprise IT has changed in less than 24 months.
Wow, that fast.
Yeah, the architecture that powered the last decade of the internet is fundamentally incapable of supporting this next decade of AI.
Okay, so to really grasp the severity of that shift, you have to look at the underlying math.
The math is terrifying.
It really is.
Yeah.
Because before the current AI boom, a standard enterprise server rack, in a standard data center, would draw maybe 10 to 15 kilowatts of power.
Which is manageable.
Very manageable. You have dozens of servers stacked together, and conventional air conditioning systems just blow chilled air through perforated floor tiles, and it handles that thermal load without breaking a sweat.
Right, because air cooling works perfectly well when the heat density is spread out.
Right.
The facility's air handlers push chilled air down these cold aisles, the server fans pull that air across the motherboards, and then the hot exhaust is pushed out the back to be cooled again.
It's a big loop.
Exactly. It's a very forgiving, predictable cycle.
But the math for AI just totally shatters that cycle. I mean, modern AI architectures housing these massive clusters of GPUs, they're incredibly dense.
Oh, yeah.
We are seeing individual chassis pulling like 5,000 watts. A single server rack filled with this hardware is suddenly demanding 30 to 100 kilowatts.
It's a massive jump.
And the documentation for the incoming hardware points to 120, even 140 kilowatts per rack. And you are basically taking the thermal output of a small manufacturing facility and cramming it into a space the size of a refrigerator.
And this is exactly where we hit the limits of physics.
Right?
Because, well, air is actually a terrible conductor of heat. Its thermal capacity is extremely low.
Okay.
So when a rack is generating 140 kilowatts of heat, you physically cannot force enough cold air through those servers to prevent the silicon from just melting down.
Wow.
Yeah. You would have to generate wind speeds so high they'd cause structural damage to the facility.
And alone the noise levels, right?
Oh, the noise would be unbearable. So for a CIO looking at their existing footprint, this is terrifying. The multi-million-dollar data centers they just spent the last decade building are suddenly structurally obsolete for the workloads the business now demands.
Right, and a CIO cannot simply requisition bigger fans.
No, definitely not.
But they also can't just walk into a board meeting and suggest, bulldozing a fully operational data center to start from scratch.
Good luck getting that approved.
Exactly. So they need a transition mechanism to keep the legacy building viable while accommodating all this new AI hardware.
The financial mandate here is all about extending the life of current capital investments.
Yeah.
You need a bridge, basically, between the air-cooled past and the liquid-cooled future.
Okay, let's unpack this because Courtney's text introduces a highly effective stopgap measure called a rear door heat exchanger, or RDHX.
Right, RDHX.
And to visualize this, you have to think about an industrial heat sink. The servers in the rack are still using fans to pull air across the components.
Okay.
But instead of blasting that 100-degree exhaust air freely into the data hall, the rear door of the server rack is replaced with this massive, tightly finned radiator panel.
The mechanism is actually very elegant because it intercepts the problem right at the point of origin.
Right.
Cold water continuously circulates through the fins of that rear door. So as the server fans force the exhaust air through the radiator, the water absorbs the thermal energy.
Oh, I see.
Yeah, so the air that eventually exits the rack and enters the room is actually just at ambient temperature.
That's incredible.
You're neutralizing the heat before it ever has a chance to affect the broader facility environment.
Okay, so the strategic value for a CIO here seems immense. You aren't ripping out the servers, and you aren't redesigning the airflow of the entire building.
No, not at all.
You are just capping the thermal exhaust right at the rack.
Exactly. It defers the massive capital expense of a total facility overhaul.
Right.
By deploying RDHX, a facility that was designed for, say, 15 kilowatt racks can suddenly support densities of 30 to 60 kilowatts within the exact same square footage.
Wow.
Yeah, it buys the organization years of operational runway to plan a purpose-built AI facility while still allowing them to deploy mid-tier AI workloads today.
I'm looking at a glaring mathematical problem here, though.
Uh-oh.
Well, we just established that the incoming wave of top-tier AI training hardware pushes 120 to 140 kilowatts per rack.
Right.
If rear-door heat exchangers cap out their efficiency at around 60 kilowatts, this bridge falls woefully short. I mean, a CIO running elite training models is going to melt an RDHX setup.
Yeah, you're not wrong. The physics of air exhaustion eventually lose to the density of the silicon no matter how good your radiator is.
Okay.
So to manage those elite training models, the cooling medium has to bypass the air entirely and get, well, uncomfortably close to the microchips.
And bypassing the air takes us straight to the bleeding edge.
Yes, it does.
The source details this shift to direct-to-chip liquid cooling.
Mm-hmm.
So we're talking about flowing fluid directly to microchannel cold plates that are physically mounted on top of the CPUs and GPUs.
Right.
You essentially trap the heat at the silicon level before it ever radiates.
And the thermal dynamics shift radically here. I mean, liquid is exponentially denser than air and possesses a vastly superior heat capacity.
So it just absorbs way more heat.
Exactly. By running fluid across a copper cold plate attached directly to the processing unit, you are removing the thermal bottleneck entirely.
Right.
This specific methodology allows data centers to safely operate racks in the 80 to 120 kilowatt range.
But the extreme end of the spectrum is what completely redefines computing architecture, and that's immersion cooling.
Oh, this is the sci-fi stuff.
It really is.
Yeah.
We aren't just putting a cold plate on a chip anymore. The entire server, chassis, motherboard, memory, networking cards, it's fully submerged in a bath of specialized non-conductive dielectric fluid.
Just dropped right in.
Yeah. There are zero fans. There is zero air.
It forces a total redesign of the hardware itself. Because every single component is in direct contact with the cooling medium, the thermal transfer is incredibly uniform.
Wow.
Yeah, the fluid absorbs the heat, naturally circulates or is pumped out to a heat exchanger, cools down, and then returns to the bath.
Okay, I want to challenge the financial viability of this, though.
Sure.
Plunging a cluster of GPUs, which can easily cost hundreds of thousands of dollars into a tank of synthetic fluid, sounds like an operational nightmare.
It sounds risky, yeah.
Right. The upfront capital cost for these reinforced immersion tanks and the specialized fluid, it must be astronomical compared to buying standard air-cooled racks.
Yep.
How many years does it actually take for this to pay off for a CIO?
Well, the return on investment is driven almost entirely by the PUE, or power usage effectiveness.
Okay, explain that.
Let's look at the financial stakes. A standard air-cooled data center might have a PUE of 1.5.
Right.
That means for every megawatt of power you spend actually running the servers, you are spending another half megawatt just running the massive air conditioning units and the thousands of server fans.
So you were burning a third of your power budget just moving air around.
Exactly. And in a 50 megawatt facility, that wasted power translates to millions of dollars in utility costs every single year.
Oh, wow.
But immersion cooling drops that PUE down to 1.05 or even lower.
That's a huge drop.
Because you completely eliminate the parasitic draw of fans and traditional HVAC systems, nearly all of your electrical spend goes directly into compute.
That makes a lot of sense.
For a CIO running AI models, 247 at maximum utilization, that extreme operational efficiency pays down the initial capital costs of the tanks very quickly.
Right.
Direct-to-chip handles your mixed, highly controlled environments, sure, but immersion is your heavy artillery, deployed strictly for maximum density and maximum long-term power savings.
But, introducing liquid into the data hall brings an entirely new category of risk.
Oh, definitely.
You can't just run industrial water pipes over rows of multi-million-dollar electronics without fundamentally changing how the facility operates.
Yeah.
The plumbing alone introduces a terrifying single point of failure.
Yeah, the transition from managing air handlers to managing fluid dynamics, it requires a complete overhaul of operational discipline.
I would imagine.
Water and silicon are natural enemies, and keeping them separated requires municipal-grade infrastructure.
And the source material highlights the critical mechanism that makes this possible, which are cooling distribution units, or CDUs.
Right, the CDUs.
Think of a CDU as a heavily fortified industrial substation. Its entire job is to create a physical barrier between the facility water, the massive rough pipes running through the exterior of the building, and the highly purified, chemically treated IT water loop that actually circulates to the server racks.
And what's fascinating here is how the CDU isolates risk.
How so?
If there is a pressure spike or a contamination issue in the building's main water supply, the CDU absorbs it.
Oh, I get it.
Yeah, the sensitive microchannels inside the server cold plates are completely protected in their own closed loop.
But even a closed loop can leak. And a leak inside a server rack is the ultimate CIO nightmare.
Oh, it's the absolute worst case scenario, which is why mitigation becomes the primary focus of facility management.
Right.
CIOs must architect continuous leak detection systems across every inch of the manifold. We are talking about sensors that can detect a pressure drop of a fraction of a PSI.
Wow, that's sensitive.
Yeah, and they're tied to automated shutoff valves that can instantly isolate a single failing rack without disrupting the fluid flow to the rest of the data center.
There is a detail in the text regarding the maintenance of these systems that is just an absolute masterclass in operational strategy.
I know exactly what you're going to say.
Right, because routine plumbing inspections, checking seals, valves, and fluid integrity that requires taking the hardware offline.
Which you do not want to do.
No. The compute time on an AI cluster is far too valuable to waste on a plumbing check. So the author points out that CIOs are aligning these liquid cooling inspections directly with the hardware refresh cycles of the GPUs themselves.
It is a brilliant optimization of downtime.
It's so smart.
You never take the cluster offline just for facilities maintenance.
Right, you wait until the exact moment you are forced to shut down the server to physically upgrade the silicon to the next generation of GPUs. So while the IT team has the chassis open to swap the chips, the facilities team is simultaneously inspecting the cold plates and manifolds. You are basically hiding the liability of plumbing maintenance inside an unavoidable hardware upgrade.
And that kind of synchronization is only possible if you have total visibility into both the IT workload and the physical infrastructure.
Right.
Which requires an entirely new approach to monitoring.
Which brings us to thermal telemetry. When people think of monitoring computer temperature, they usually picture like a basic thermometer readout.
Right, like on your laptop.
Exactly. But at this scale, a temperature sensor is basically useless. By the time a room-level thermometer registers a heat spike, the silicon has already throttled down or sustained damage.
It's too late.
Way too late. The telemetry required for liquid cooling is more akin to an industrial SCADA system monitoring a power plant.
Yeah, you are shifting from tracking static temperature to tracking dynamic heat flux.
Heat flux.
Yeah, you need to map the exact movement of thermal energy across the heat exchangers, the fluid velocity inside the cold plates, and the pressure differentials across the pumps in real time.
Okay, so the strategic advantage here is the shift in posture. You are moving away from reactive firefighting.
Precisely. A reactive posture relies on an alarm going off because a server is actively overheating.
Right.
Proactive telemetry allows the management system to identify, say, a microscopic decrease in pump efficiency or a slight degradation in heat transfer across a specific cold plate weeks before the temperature ever reaches a critical threshold.
Oh, that's huge.
It is. The CIO can schedule targeted maintenance during an off-peak window, ensuring the environment remains perfectly stable.
So what does this all mean? If you are an IT leader, you have to build a business case for these massive physical changes.
You have to justify the spend.
Right. The article distills this down to a CIO's scorecard, built on 3 central pillars: uptime, cost, and sustainability. So we need to evaluate how these cooling architectures actually deliver on those metrics.
Okay, let us evaluate uptime first. The defining characteristic of AI workloads, particularly inference models, is unpredictability.
Right. You don't know when the requests are coming.
Exactly. A system might sit at 20% utilization and then instantly spike to 100% when a massive query hits.
Okay.
Air cooling really struggles to adapt to instantaneous bursts of heat. The thermal mass of liquid, however, provides this incredible buffering effect.
Oh, because it takes longer to heat up.
Yes, liquid cooling absorbs those massive thermal spikes instantly, maintaining rock-solid temperature stability, which directly translates to hardware longevity and higher uptime.
That makes perfect sense. The second pillar is cost, which is where the internal battles are fought, I'm sure.
Always.
We touched on the OpEx savings of immersion cooling, driving down the PUE, but the source details another fascinating cost mechanism regarding the actual temperature of the water used in these loops.
Yeah, this is a big one. Legacy data centers rely heavily on mechanical chillers to drop the water temperature down to like 45 or 50 degrees Fahrenheit.
Like a giant refrigerator.
Exactly. And running industrial refrigeration is extraordinarily expensive.
Right.
But because modern GPUs run safely at much higher internal temperatures, often approaching 180 degrees Fahrenheit, the water used to cool them does not actually need to be mechanically chilled.
So you can run 90 or even 100-degree water through the cold plates, and it is still cold enough relative to the GPU to effectively absorb the heat.
Exactly. By utilizing warm water loops, facilities can bypass those expensive mechanical chillers for most of the year, relying solely on passive dry coolers up on the roof.
Wow.
The reduction in the facility's overall energy consumption is just massive.
And here's where it gets really interesting, because that warm water loop feeds directly into the final pillar: sustainability.
Yes.
Historically, data centers have just vented their thermal waste into the atmosphere.
Just blowing hot air into the sky.
Literally. But when you are capturing 100 kilowatts of heat per rack into a contained fluid loop, that water exits the facility at a highly usable temperature.
You transform a waste byproduct into a commodity.
Right.
That high-grade thermal energy can actually be routed into municipal district heating systems.
That is so cool.
A data center running AI models can theoretically pipe its exhaust water to heat adjacent commercial real estate, greenhouses, or manufacturing facilities.
I love that.
It completely alters the carbon footprint and the public relations narrative of the data center.
Looking at this scorecard, the role of the CIO has fundamentally expanded.
It really has.
10 years ago, an IT leader could just hand a spreadsheet of power requirements to the facilities manager and tell them to keep the room cold.
Not their problem.
Right. But that separation of duties is dead. The choice of cooling architecture, RDHX, direct-to-chip, or immersion, dictates exactly what kind of compute density the business is legally and physically allowed to operate. Infrastructure is no longer a support function. It is a hard cap on the company's AI capabilities.
The physical layer and the application layer are inextricably bound together now.
Yeah.
A brilliant AI strategy is entirely worthless if the building cannot physically absorb the heat of the required processing power.
And the pressure is only going to intensify. The final section of Courtney's text outlines the incoming wave of hardware, and the numbers are just staggering.
They're hard to even comprehend.
We are preparing for facility designs utilizing inlet water temperatures of 40 to 45 degrees Celsius. We are looking at modular immersion pods engineered to handle a mind-bending 200 kilowatts per rack.
Unbelievable.
And the silicon manufacturers are developing new GPU fabrics that will push power density well beyond current thermal envelopes.
Which really raises an important question about the limits of human management.
What do you mean?
Well, as we push toward 200 kilowatts per rack, the complexity of managing these fluid dynamics, power routing, and thermal telemetry, it just exceeds human reaction times.
Oh, I see.
The most profound detail in the source material points to the deployment of AI-driven facility controls.
Wait, the software managing the physical building?
Exactly. We are entering an era where the telemetry data from the cooling loops, the pressure sensors in the CDUs, and the utilization metrics from the server racks will all be fed into a localized machine learning model.
Wow.
That model will autonomously adjust pump speeds, route power dynamically, and predict thermal failures in real time.
That is the ultimate recursive loop. We are building these massive, physically extreme structures specifically to train and house artificial intelligence.
Right?
And we have reached a point where the only way to safely operate those structures is to hand the facility controls over to the AI itself.
Yeah.
The intelligence running on the servers is simultaneously managing the fluid dynamics required to keep itself from catching fire.
Yeah.
The machine is actively learning how to manage its own life support system.
The boundary between the digital intelligence and the physical facility just dissolves. The data center ceases to be a building housing computers and becomes a single, self-regulating organism.
That is an incredible concept to walk away with. We began this deep dive attempting to drag the ethereal concept of the cloud down to earth, exposing the brutal, heat-generating reality of physical hardware.
Which we definitely did.
We really did. But the solution to managing that physical reality requires an architectural sophistication that is just as advanced as the software it supports. The physical infrastructure behind our digital world is not just keeping pace, it is evolving into a discipline of extreme engineering. Now, thank you for joining us on this deep dive. Take a moment today to consider the immense physical machinery silently running behind every query you make, and we will catch you next time.